So let's get started. So today's, have all of you seen groups? Have you seen some group theory? Okay, good. So today we will start from a special kind of group called a braid group. Okay, and before I define what these groups are, I'll just tell you what they are as sets. What are the set of elements which make up the braid groups? In particular, I'll tell you what are the set of braids. So, to define, so this is the first section of my talk, braid groups. So in order to define them, you take a natural number, one, not zero, so 1 or above, and define a set Bn to be the set of braids on n strands. I'll tell you what these are using pictures. Okay, so here, in this picture here, everything in the first row, there are 4 pictures in the first row, and these are all elements of B2. So these are braids on 2 strands, which means that there are 2 strings traveling downwards. The strings always travel downwards, and they can cross each other. And they can there are 2 ways they can cross each other. They can cross each other like this. The left one goes on top, or they can cross each other like this. These 2 are different elements. Okay, so we count, an element in B2, which is a braid on 2 strands. Braid on 2 strands is what? Is one of these pictures. Take 2 strings and make them travel down, and in the middle they can do any number of crossings that they want. So each of these is a braid, and these are braids on 3 strands. So these are elements in B3. Okay, now you may think that there is just way too many ways of drawing them. For example, what if I move this crossing slightly up? Are these 2 the same? So we don't want to distinguish between these too many different kinds of things. So let me erase this. So there is one other thing which is part of the definition. 2 braids are equivalent, or you can think of them as the same object, are equivalent if one can be deformed to the other without moving the endpoints. You can all read this. So 2 braids are equivalent if one can be deformed into another without moving the endpoints. So let's draw some examples of equivalent braids. So the simplest kind of examples are these. This is a braid on 2 strands, and I go slightly lower and cross. This is also a braid on 2 strands, and I can just pull this crossing down continuously, and this becomes this. So I'll say that these 2 are the same object. So this is the simplest kind of equivalence. Now you take out your worksheets, and the first problem is what we will work on first. So each in 1, 2, 3, 4, in each of them there's a set of braids, and you have to say which of them are equivalent and which of them are different from each other. So we can start with number 1 now. In B3, second one, yes, very good, you're paying attention, yeah. Now is it okay? Very good, okay. So let's start with problem 1, okay. Problem 1, part 1. So there you see 2 pictures of braids. and you have to tell me whether they are equal or not, and one person will answer each of the questions. So anybody who is ready to answer can raise their hands. Yes, they are not equivalent. Why?
Because it can be immediately same. So the first case, the higher single strand is
Let me just draw one picture here. So this is the first one, and this is the second one. And why are they not equivalent?
because the left two are entangled and the right two are entangled.
Yes, yes. So that's so you can say that this one is not crossing at all here, whereas here this one is going across. So so you can say that if you number these starting points as 1, 2, 3 and ending points as 1, 2, 3, this braid is giving me a permutation. A permutation is something you saw in the first class, right? So in the first braid, 1 goes to 2, 2 goes to 1, and 3 goes to 3. In this one, 1 goes to 1, 2 goes to 3, and 3 goes to 2. So it is very obviously at a combinatorial level, these two cannot be the same thing. So they are not equal. Okay, but we won't always be able to do this. So let's keep going. What about the second problem? In the second problem, there are two entanglements, and one is above, one is below. In the other one, they are both at the same level, right? So they are the same. So we can just move these crossings up and down, like what we did in the very first example here. So in 1, 2, they are equal. What about 1, 3? There is 3 of them. We have to say which of them are equivalent, which of them are different. A and C are very good. Yeah. So this is getting slightly tricky to see because this is 1 and we say that this is the other, because we can take this loop and just start deforming it. Do something like this, then do something like this, then it becomes straight. So in part 3, A and C are equal. And what about B? What about B? B we cannot do that. So B, if you try to do it, it will just get tangled up. So B is different from A and C. And let's yeah. In which one? On the board. B2. Are they the same? What do you think? So these two are the same. They are the same picture. No, are they the same? Are they the same? They are not. One is an overcrossing, one is an undercrossing. So they are different. So all 4 are different in that B2 picture. One minute, I'll answer your question. Yes, what's the question? Yes, that's a good observation, and we are going to get there very soon. Yeah. Okay, and okay, so let's keep moving. What about the fourth, 1, 4? Is there anybody without a sheet? If so, you will be lost by now, so please ask for the sheet. So 1, 4, which of them are the same? Yeah, this is the hard one. You have to look at them carefully and see if you can change one to another. A and B. Okay. And the others? So let's draw A and B on the board. This is one of them. So this is A and this is B in problem 4. And we think they are the same. Does anybody disagrees here? Anybody, if you have a question also you can ask. How will you move it? If you have to move A to B, what will you do? Why don't you, one of you can come up and draw some intermediate strand in the deformation. Like when I say a deformation, there are these intermediate pictures, right? These dotted lines which take you from one to another. Does someone want to come up and draw one strand? How to move from A to B? Come.
Completely below.
Huh.
So you can keep that aside, so it kind of slides from below.
Okay. Okay. It slides from below. Yeah. So it will slide from below, but it will go upward in the board, right?
What I did was I just took it out.
Oh, you can't take it out because you have to keep the endpoints fixed. So that is a constraint.
So okay. So what my logic was that this one is above on all the knots.
Yes.
And this one is below on all the knots.
Yes.
The one in between should be above the one below and below the one that is above all the knots.
Okay, so you can kind of, yeah, you can imagine as if this is in a top plane, this is in the middle plane, this is in the bottom plane, and you don't have to move the endpoints, but you can move the braids around. Okay, yeah, that's a very good way of looking at it.
So then you see that the same thing works here.
Correct, yeah, yeah, thanks, that works. Let me try to see if I can, any other comments? Yeah, that works, thanks. Any other comments or answers? Yes? Okay, so her way of doing it is like, although we have drawn it all on the blackboard, we can imagine as if this top one, let's say this is the orange one, this is on a parallel plane which is slightly above, and then we have a violet one. This is not very violet, let's draw a pink one. Yeah, there's a pink one which is in the middle plane, and the white one which is in the lowest plane. And we can just keep the endpoints fixed and move each of them in their own planes to get this drawing. So that was what her observation was. But if you want, you can also draw some of the intermediate diagrams. So for example, let me just move the pink one. So the pink one will become above, crossing above, like this, and then it will move closer like this, and then it will cross from below this crossing to the other side, and then it will become that drawing. So there are various ways of seeing this. So in fact, if you want, you can, when you go home, just take 3 threads, place them like this, and if you will be able to, and make sure to put tape here. These are fixed, you cannot move them. So this picture is not the greatest because this dotted one has to come back here. So keep the endpoints fixed and you will be able to move from one to another. And a nice way of seeing it is this planes way which she just said. Okay, and any questions? Yeah, that's what I was trying to do. These dotted ones are the intermediate ones. This pink one, I move to this dotted one, and then it moves here and it goes past this crossing. So the pink one is this one. So it has gone past this crossing. Yeah, the crossings will remain, but they are kind of interchanging the order. Anybody, if you don't understand, please ask. In B2, here, these two are not the same. Because here, this we can say at the level of the permutation. 1 goes to 2 and 2 goes to 1. Here 1 goes to 1 and 2 goes to 2. So just from that, we can deduce that these two are not the same. Yes, that doesn't work most of the time. That is a very coarse kind of logic. But this is more finer. These are actually the same. So you have to show how you can move from one to another. Yeah, that is the same. So even that could be the same and the knots can be different. For example, here the 1 goes to 2 and 2 goes to 1 is same here and here, but these two are different knots. Okay. Okay. More questions? And what about 4C and 4D? Are they the same as A and B? No. Yeah, so when you can't slide. So here you are sliding one of these. This one you are sliding from between the crossing and taking it to the other side. You can do no such thing in C and D. So C and D are different. So these are not equal to C and not equal to D, which are also different from each other. Okay. Okay, so let's move on. So now we know what the set Bn is. Okay, so we have defined Bn as the set of braids. And the next thing I'm going to define is a multiplication operator on Bn. So define a multiplication operation on Bn. And what this operation does is it just concatenates braids. So for example, I'll just show this via an example. So this is an element in B3. And let's take another element in B3. So I'll tell you how to multiply these two elements. And the way to multiply it is place the second element below the first element. So maybe again let me use colors. So this is equal to the white one above, and then follow it by the orange one. So that's how you multiply braids. Okay. So now, so that is one definition. The other definition here is, if you're talking about multiplication, maybe there is an identity element also. Can you guess, is there an element in Bn which will not change the braid? The trivial braid, yes. So this, the parallel strands, correct. So this is definition A, and definition B, let's go, no, B here. Identity element is the trivial braid. So what is the trivial braid? Which is, it just consists of, i.e. parallel strands. So this guy here is the identity element, 1. And that's reasonable because if I do this followed by that, the braid doesn't change, right? So therefore, that is the identity element. So what is so in B3, what is the identity element? 3 strands. So it's a braid which does nothing. It's from top to bottom, there are no crossings. It just goes straight. Okay, so now we know how to multiply and we know what is the identity element. Now the next question is is this a group? So what do we have to do to check whether this is a group or not? So it's actually a theorem. Let me write it down. Bn is a group. So in order to show that Bn is a group, what do I have to do? Louder. Closure. So yeah, so if you multiply two braids, you should get a braid. That kind of follows from how it is defined. That is fine. Then what else do you check? Associativity, right? So you just have to check if there is three of them, it's one after the other after the other. So that is also obviously satisfied. Then it has an identity element. Inverse. Inverse is one thing we need to check. So let's try to construct some inverses. And here, let's try with the simplest braid, okay? So the question now is, does there exist an inverse? So let's start with the simplest example in B2. And we have to multiply something to this. We have to place something here so that it becomes the trivial braid. So this is the identity element in B2, remember. So what can I place there so that it becomes this? 1 minute. Somebody new person? Yes, you want to? Yeah. Replace the undercrossing by an overcrossing. So if I do this and multiply, I get something like this. This is the effect of multiplication. And then I can just pull the top strand and it becomes the same as that. And note that I am not moving the top and bottom. I am just taking this and pulling it. So it becomes that. So that is how you produce inverses. So we have done one example. Let's try to do some more. And these are there in your sheet. So we have just done 2A. So can you think in a similar way and do 2B? Construct an inverse. So what we have just proved is this. The inverse of this braid is equal to, this guy. This is what we have shown so far. So do a similar kind of logic and try to do the next problem, 2B. Are you done? The back? If anybody is done, they can raise your hand. You're done? Okay. Why don't you come up and tell us what it is? Let me clear some space for you. Right. Sure, I can just draw it for you. Here. So you're trying to, if we can just use more space.
I think it's fine.
Yeah.
So I was just thinking of it as flipping it upside down.
Uh-huh.
So this one comes this way.
Okay.
And then you want it to be under that side. And then the other one sort of fills itself.
Right. Yeah, that works. Yeah. So what we have seen is that the inverse of this is its mirror image. No. So this part is the inverse. So yeah. Okay, so one way of thinking about this is just a second. So let's focus part by part, okay? So let's just take two of these crossings. Let's draw a box around two of these crossings, okay? And you focus on what is inside. So here, this strand is going on top and then coming back on top. So can you deform it to something simpler? Yes, you can undo it. So let's draw that. So if I pull the strand back, I end up with this one goes here, and the other one is just that. And above, we are left with this and okay. So we have unentangled one thing, and then this now we are in the same picture as this. We know that this guy is the inverse of that guy. So we are back to the same picture. So when calculating the inverse, you can break it up into horizontal parts and do each part. So start with the bottommost part and find the knot which undoes that, does the reverse of that, and then keep going to the top. So let's maybe do one more example here. So, or does anybody want to do example C? If you see how to do it. Anyone from this side? Yes, come. So let me start, you can just start by drawing the original thing, which is here. Yeah, you can draw the inverse straight away. Maybe draw it below, then it will be easier for people to see if you just draw it here. Yeah. Okay. So so this is the knot and this is the inverse. Okay, so these two will cancel out, and after that, yes, right. So this is a undercrossing or overcrossing? Okay, good. Okay, thanks. Maybe do you want to say anything about how you arrived at this?
That image, mirror image, we can just...
Mirror image, okay, okay. So you are, okay, that works. So, yeah, the mirror image seems to work, but you can also think of, yeah, so he has literally drawn the mirror image, which works fine. But when you mirror, the closest one to this line will also be the closest one to the boundary. And so these two will unknot, and then these two will unknot, and those two will unknot. So let me just draw a slightly different picture of this. No, actually, this is a different example. So when I'm trying to find its inverse, first I will invert the last crossing. So then what that means is that, So if I combine this and this, it will become a trivial knot, right? So like these two together are a trivial knot. So now I have to undo this guy. So for that, so this is the inverse. So it is the same as taking mirror image, and what the mirror image is actually achieving is that one by one the crossings are getting cancelled out. So whatever crossing is the bottommost will be the topmost, and then those two will cancel out, and so on. So first this bottommost one will cancel out, then the top one will cancel out. Here these two will first cancel out, then the middle will cancel out, and then the top will cancel out. So at every step you can just disentangle the strands and get the trivial braid. Okay, yeah. 1 minute. In the C part, yeah. Yes, yes. Correct. Yeah, yeah. You can also do that. But I kind of want to emphasize that as an algorithm, the mirror image is a fine algorithm. Another algorithm is to do one by one in reverse order. Okay, so you know how to calculate inverses, and so we have also convinced ourselves in this process that inverses exist because we have come up with an algorithm to write down the inverse. So therefore, an element in Bn always has an inverse, and we can conclude that Bn is actually a group. So we have checked that inverses exist. So therefore, Bn is a group. So we have shown that Bn is a group. So we can start calling it the braid group. Yeah. Can you be louder, please?
Is this abelian?
No, it's not abelian. We'll see that very soon. Good question, yes. Okay, so now we'll explicitly start computing some of the braid groups. So example, let's start with B1. What are the elements of B1? Yes. So how many elements does B1 have? 1, because there is no crossings possible, right? So there is only a single element which looks like this. And this is the identity element. So it's a trivial group. It's a group with only the identity element. Now let's come to B2. So let's start drawing lots of elements of B2. So what's the first element of B2? Huh? Yes, this is 1. Next, overcrossing, then undercrossing, then huh? Double overcrossing, double undercrossing, yes. So 1 overcrossing, 2 overcrossings. Then similarly 1 undercrossing, 2 undercrossings. And then, can you combine 1 over and 1 under? Let's see. So what order should I do it in? Let's do 1 over and then 1 under. This is an element? Yes, this is the same as this. So whenever you have an over and under next to each other, you can disentangle it. So we can't have over next to under. So either it will be all overs or all unders. So now you are starting to get a sense of what are the elements. How many elements does it have? Huh? Do you want to say? Are you? 5. 5. No, I've only drawn 5. Are there more? Which one? Can you say one more? 3 times. So I can keep on going, no? So how many elements are there overall? N, yeah. So any n I give you, you can draw something with n crossings. How many of you, there's n under crossings, n over crossings, right? Okay. So we have a good sense of this, but this is actually a group. So let's think in terms of generators, okay? So is there a generator for this group? Have you seen generators of groups? You have, yeah? Okay, so his suggestion is let's take these two. Actually, let's just start with 1 and see how far we get. Okay, so let me erase part of the board. So let's call G as a braid with 1 overcrossing. This is an element in B2. And let me write down powers of G. So this is G. What is G square? How do I multiply? Remember, I take 2 copies of G. So what is this? Have you encountered this before? Yeah. There, right? Yes, this one. So this is G, this is G square. So 2 overcrossings is G square. What is G cube? 3 overcrossings, yes. So G to the n is going to have n overcrossings. So you have produced everything with overcrossings. All the braids with overcrossings you have obtained. Now let's look at what about G inverse? Yes, G inverse is undercrossing. That's the first example we did, remember? So G inverse is the undercrossing. And then what is G to the minus n going to be, where n is a natural number? N undercrossings, right? Yeah? Infinite cyclic group, perfect. Isomorphic to Z, exactly. Okay, so have we gotten everything? Let's check. We have gotten everything, right? So what about the trivial one? That's the identity. That's already there. So if you start with this 1G, its powers are going to give you all the elements of B2. So therefore B2 is generated by G and it's isomorphic to Z. Can you raise your hand? I don't know who is talking. Yes, yeah. Huh. Huh.
It can't generate the elements generated by G inverse, right?
No, that is when you say group subgroup generated by G, you are also taking G inverse. You don't have to count G and G inverse as separate generators.
Okay, so every
That is
time
kind
you
of, that's a definition actually of what it means to be generators.
So technically it would be G inverse are the
Exactly,
is the set of the
yeah, and all
generators.
combinations of that, yeah. No, so by definition, when you say what is the group generated by G, you are taking G inverse also in there. You are allowed negative powers of G also. In a finite group, you don't have to consider that because some positive power will also be a negative power. Like if you take Z5, then G to the 4 will be same as G inverse. So then you don't have to consider that. But in the infinite case, you have to consider G inverse separately. Yeah, exactly, yeah.
Ma'am, how is G isomorphic to Z?
Okay, how is it isomorphic?
Okay, so you say that
So we will.
is 1, 2 not is 2.
So, what is a group operation in a set of integers? Plus, yes.
Multiplication.
So here it is multiplication. So I will give a map from Z to B2. So what will I send 1 to? 1 is sent to what? No, parallel strand is 0. Yeah?
1 not. So
1 is sent to G, correct. That works, yes. 1 is sent to G, and in general, n is sent to G to the n. And this is a group isomorphism. Note that 0 is sent to the parallel strands. Okay. So this is a group isomorphism. So you have the addition here and the multiplication there.
then G inverse should also be part of the group. Right?
Yeah, so G inverse minus 1 will map to G inverse. So this n goes to G to the n captures everything. Okay, are we very sure what B2 is? B2 is same as this integers. So it's an abelian group. Yeah. You have a question?
It's abelian, right?
Yes, it's abelian. Yes. Okay. Now, the next example is B3. B1 is trivial. B2 is the set of integers. B3, let's think of B3. Let's start warm up. Let's draw some elements of B3. Huh? Firstly, parallel strands, yes. Then, okay. One overcrossing, one parallel. Then, yeah. Then, yeah, say it again, sorry, louder. Yes, same kind of things we can keep on doing. And so on. But soon you start to see that we can start drawing combinations also. We can do this followed by that, right? Overcrossing, overcrossing. And there we said, what about can we combine overcrossings and undercrossings like this? Like this? Is this allowed? Is this trivial? Can I simplify it anymore? No, right? Earlier we said over and under will cancel out. But here, that's no longer the case. You can do over in one, under in another. They are not going to cancel out. So suddenly, it's a much more complex group. So it's going to take us a long time to get at this kind of a list. So we have to be slightly smart. So in the end, any strategies of how, I don't want to sit and list everything. It's going to take forever.
Actually, we can first check when the endpoints at this become. Suppose if it's we have 3 upper endpoints, lower endpoints. First, we'll check how many endpoint. What I'm saying. Actually, suppose take this as A, B, C. 3 strings are.
1 minute. Let me start drawing what you're saying. Just hold on. Yeah. So you said A, B, C, yes?
Okay, here D, E, F for bottom. Okay, we'll first take a string as from A, if you join A to D, B to C, E, and E to F. This is one string.
That is this one.
Yeah. And then just swap the ends, A and E, B and C.
A and E, yes, yeah.
Join. Like that, first we can say all the combinations, or what are the endpoints we can join.
Yeah, so you are saying that, in some sense, what you are saying is, we can break this up. You can think of this composed with this. Is that what you're saying?
No. I'm saying that what are the possible ways means, all the possibles are, from first we'll fix what are the endpoints, what are the possible endpoints, and then what are the over and lower that not.
Yeah, but then the possibilities are huge, right? We have to write them in an efficient way. I understand what you're saying, but when you start actually listing, it will be a really big list. And it won't be even a nice list like this. Because you can have under, over, under, this side, that side, everything. So is there a neat way of thinking about this? Yes, we will use these partitions and then?
We use those 4 ones originally which we made, one parallel.
Yes, exactly. You are on the right track. And the 4 ones we originally made, those are what? They are the generators. So let's come up with generators and see how far we get. Right. So his idea is, let's think of these as some kind of primary elements and we will combine them. And our observation is that we don't even have, these two are not separate generators. This is just the inverse of that. That is just the inverse of this. So how many generators do I need? 2 generators, correct. Okay, so let's give names to our generators. Let's call X as this guy, Y as this guy. And can we, so now let's come to the third problem in your worksheet. So 3A and 3B we have already done. So let's move to 3C. So I have given you 2 generators. So these are both elements in B3. And now your goal is in 3C and 3C, D, E, F, all these 4 problems, write that braid in terms of generators. So when I say generators, you are allowed to use X inverse and Y inverse also. Those are also at your disposal. So use all of those and try to write these 4 braids as products of X, Y, X inverse and Y inverse. Yeah. 1 minute. Just work others out so that people have more time. Yeah, you're right. There's no Z though. It looks exactly like this, right? So it's just an X. Okay, so let's do 3C. So I'm going to draw it in a way which tells you what the answer is. So C can be written like this, right? What's the top one? X. What's the bottom one? Y. So this element, this braid is exactly XY. And then similarly, what is D? D you break into 3 parts. Hi, sorry, say, yeah?
Y inverse and X inverse.
D is, why is it inverse? It's still the same kind of crossing, no? Like, let's draw that. It is this, followed by this, followed by this. So this is X, this is Y, this is X, right? So this is XYX. And what is E? Yeah, it is yxy. And f is y. Correct. Here is where you first see the inverse. So the bottommost crossing in f is the reverse of that one, so it's an inverse. Any questions about this? Okay, so what this is kind of telling you is that any braid in 3 strands, you can write it in terms of the generators x and y. So it tells you, we can conclude that B3 is generated by x and y. So now do we know B3? Is there anything else we need to know? So that's it. We know B3. Is something missing? So who has taken, have you studied group theory in your BSc or MSc? You have studied in MSc? Yes. So if to describe a group you need generators and what else? Relations, yes. You need relations. So there might be some combinations of x and y and x which is just the same as some other combination of x, y and x. So we need to be aware of those also to fully understand this group. So those are relations. Okay, and this is a little hard to guess on your own. So let me just tell you what it is. There is a certain So we did this in the beginning. One of you came to the board and said, yeah, you came, I think, right? No, it was you. I forgot. Who said there was 3 different planes and yes, you said. Yeah. So this one and the equivalent one is sorry. Yeah, so this is an example we discussed earlier, and we saw that this strand here can be moved across the crossing to become this strand. We saw this example earlier. We saw that these 2 things are the same. Do you remember from the beginning of the lecture? So, and how do you write this in terms of x, y, z? What are these 2 things in terms of x, y, z? Sorry, x, y, yeah. This is x, y, x, and that is? Yes. These 2 things are the same. So this is a relation in this group. And in fact, with some work, you can show that this is the only relation. And therefore, B3 is generated by 2 elements and it has 1 relation. So a fairly complicated group. It's hard to write everything down. It'll take a long time.
This is somewhat like similar to there's an infinite diagonal group.
It has a similar flavor, but there are, I think this group, it's a probably bigger, yeah. Yeah. So this is a non-abelian.
Conjugate relation?
Huh?
Is this one is conjugate to other means, right?
Yeah.
The relation is nothing but it's a conjugate to each other, huh?
This is, I think this conjugate is not the word. This kind of a move where you move a strand past a crossing, it's called, in the knots literature, it's called a Reidemeister move. And this is kind of studied in physics also, and there they call it a Yang-Baxter equation. So it is known by different names, depends on where you're coming from. So this is called a Reidemeister relation. Okay, so this is B3. Let's move on from here. And in fact, using this technique, we can write down any braid group. So let me just do B4 and then. So any questions about B3? Louder, please. So if a free group on 2 elements is just all words you can write down whose alphabets are X, Y, X inverse and Y inverse, right? But there are some words which are same as the other words. So it's kind of an equivalence relation on the free group. So, and that is the relation. So wherever you see an XYX, you can replace it by a YXY. Like what? Yeah, this is an equivalence relation in if you can think of this B3 as all words in X and Y modded out by an equivalence relation. So this is, you can think of this as an equivalence relation. Wherever you see the string XYX, you can replace it by YXY. No, that is not true. So the symmetric relation does not hold here. If it held, this would have been an abelian group. But this is not, that is not the case. XY is not equal to YX. Yeah, so that is a different kind of relation and it will give you a different group. Any other questions? Yes, it's not abelian. Yeah. So this is. So it's a non-abelian infinite group. Yeah.
We can define group action also because we form a group. We can take another set and we can define here group action.
You mean group action of B3 on something else? Sure. Yeah, why not? Huh? I don't know. I haven't thought about it. What is the sense? It's probably trivial. That's my guess, but I'm not sure.
If I think it to be of the same flavor as director group,
Huh.
then the center is from the same flavor is coming to the trivial one.
Okay. Okay. Yeah, I think that's probably right, but I haven't checked this. Okay. Yeah. Which type of what we can consider? I don't know, that is up to you. I think there is a easy thing which you can do. You can consider the action of the permutation group and that also automatically gives an action of the braid group. But then that misses the complexity of the braid group. The braid group is much more complex than a permutation group. But there might be other group actions which capture some flavor of the braid group also. Huh. Huh. So you are saying that what acts on what? Group. Yeah, you are taking the B3 and acting on what? What? Yeah, maybe there is an action. Sure, why not? Yeah. Yeah, in fact, like in B3, you can just forget one of the strands and you get B2. So, and then you can just multiply by B2. So that gives a B3 action on B2. Okay, so let's move on from here. So in the next part of the talk, what we are going to see is that we are going to define this braid group in a completely different way. Okay, so let's get started. So where are we headed? We are headed towards giving a different viewpoint of the braid group. And in order to give this different viewpoint, I have to introduce a notion which some of you may have seen in your classes. And that is the notion of the fundamental group of a topological space. of you have seen fundamental group? Raise your hand. Oh, not many. Good. I assumed you wouldn't have seen, so I've prepared for that. So let me tell you what fundamental group is. So let X be a topological space, and let's take a point on X, and we will call, this is any point on X, and we'll call this a base point. So this is a definition, okay? So I am going to define a set called pi1 of x comma x. It doesn't have a name yet. We'll just call it a pi1. And what is this pi1? It is the set of loops in X that start and end at little x. So the kind of topological spaces you should think is not some crazy topological space, something easy, okay? So let us think of, my favorite example is R2 minus a single point. Take any point. Okay, this is going to be my example. So R2 this is R2, and take out a single point. This point is not there. So this is my topological space, and I can choose my X as any point. So this point, since it is missing, let me draw it in a different color. Something close to red, because it's a no-go. You cannot go in there. Usual topology. Yes. So this is, now we are going to think about loops that start and end in X. So these are some loops. So you travel and come back. But make sure you don't go to that point. The pink point is not there in the space, so you cannot go into it. So the set of loops looks like this. But again, with braids we saw that we can't just make some tiny deformation and say this is a new element. You cannot do that. So there has to be some equivalence here. So that equivalence comes from here. So I'm continuing the definition. Two loops in pi1 x comma x are equivalent if one can be deformed to the other without changing the endpoint. So this is the definition of pi1 x comma x. So it consists of loops, and many of these loops are the same as the other.
Ma'am, then only there are two loops, right?
Yes,
Two
there's
classes.
much fewer than you would initially think, but we'll get there in a second. Okay, so I'm going to draw many loops, and you are going to tell me which are all the same as the others. Okay, so similar exercise as before. So let's start with this loop, and this loop. Are they the same or different? Same, because you can start shrinking this and you become that, okay? And you can go on shrinking. So what is the simplest way of expressing this loop? You can just stay at the same point. That's also a loop. Okay, so when you think of a loop, you should think of a continuous map from the interval to x. Continuous map such that the endpoints gamma 0 and gamma 1 are both x. So this is what loops look like. And nobody is telling you to move. You can just stay in the same place and call it a loop. So gamma can be a constant loop. This is also a loop. Let's call that gamma 0, and gamma 0 just lives here. Okay, so let's call this gamma 1, this is gamma 2. So let's draw an even bigger one, gamma 3. Are all these the same? Anybody disagrees? Okay, good point. Arrows don't agree. Gamma 3 is going in this direction, gamma 1 is going in this direction. But it doesn't matter because I can shrink gamma 3 to a point, I can shrink gamma 1 to a point. So they're all the same. So all these loops are the same. Okay, now let me do something else. Let me go all the way round and then let me come back. So this whole thing is a loop. It's starting from here, going here, and then touching x0 and then coming back. And let's call this loop, let's give it a different color. Sorry, yeah, it's going all the way to x0 and then coming back. And let's call it gamma 4. Is gamma 4 the same or the different as the constant loop? Yeah? Yes. In the middle, if I touch x0, it doesn't matter. Only at the endpoints, you have to keep it fixed. So what I can do is, you're all right, that I can start deforming it. So I can not go all the way, I can go part of the way and then start coming back. Then I can go less and then come back. I can keep doing that, and I can eventually deform gamma 4 to the constant loop. So we actually see that gamma 4 is also in the same category. Okay, now can we draw something which is not the constant loop? Let's try to get something different. So what should I try? Don't come back, yes, very good. Let's do that. Missing point x, let's call this something else, alpha 0. So alpha 0, you cannot deform it to the constant loop because this point is missing. So if you start shrinking it down, you will hit this point, and since that point is not even there in the space, you cannot deform it. So this and okay, now can you produce more elements which are different from all this? Huh? Yes. Okay, so before we get into all that, I want to give you one more definition, which is, eventually I want to make a group out of this. So I have to give you a multiplication operation. So if I have two elements in this pi1 x comma x, their multiplication is go along alpha 1 and then go along alpha 2. Go along alpha 1 and then go along alpha 2, right? So what you said, we can go around twice. So this is different from anything we have seen before. But can we obtain it by this kind of thing? What if I actually make sure I come back to x and then start? So I go around, come back to x once, then go around, come back to x once. Then can you write it in terms of alpha naught? Yeah. So this is exactly alpha naught multiplied by alpha naught, or in other words, it is alpha naught square. Okay. Now can we come up with other elements? This is going in a very similar direction as something we've already seen. Yeah. So,
All the loops generated by alpha naught.
Say it again.
All the loops generated by alpha naught.
Yes. So so we can go around this whole n number of times, and we'll get alpha naught to the n. What about the negative n's? How do you write alpha naught inverse? Opposite direction. Good. This is x, go in the opposite direction. This is alpha naught inverse. So whenever you have a loop, if you go in the opposite direction of the same loop, that's the inverse. So all this tells us that pi1 x comma x is a group. And in this particular example, what is pi1 x x? What is this example? It's just z, right? It's very similar to the second braid group. You just see that it is z. So where you take any integer, if it's a positive integer, you go in a counterclockwise direction n number of times. If it's a negative integer, those many times you go in a clockwise direction, and you see that the fundamental group is Z. And this group is called the fundamental group. Of x. Okay. Now, I don't have too much time left, so I have to get to my point, which is how to see the braid group from a different viewpoint. So for that, I'm going to take a very strange x. So let's braid groups via configuration spaces. So I'm going to tell you what a configuration space is. So again, n is a natural number. So I'm going to define a set called conf nr2, which is the configuration space of n points in R2, configuration space of n points in R2, denoted by conf nr2, and this is just a set of n unordered points in distinct points in R2. Okay, so you can think of this as a set of endpoints. In a set, an order doesn't matter, right? If I have x1, x2, x3, that I can write it as x2, x1, x3. It is the same set. So you can literally think of this as a set of n points in R2. So example, if I take 3 points, 0, 1, 0, 0, 1, this is an element in conf 3 R2. And I can switch the order, it will continue to be the same element in R2. Any questions about the definition of configuration space? It's a very simple definition. It's literally sets, subsets of R2 with n elements, that's all. Every element has n points in it. The order doesn't matter. Now, we are going to look at what is the pi1 of conf n R2. Okay, so recall that pi1 is, we have to choose a base point and we have to look at loops starting and ending at that point. Okay, so let's do that. So let me draw my R2 like this and just take these 3 points, 0, 0, 0, 1 and 1, 0. So how to think of a loop here? In this space you could just draw loops, but this space is a bit more complicated. We can't just draw it. So the way I'm going to think of a loop is a continuous map from the interval to this conf 3 R2. So in this example, n is 3. So that it starts and ends at the same point. So gamma 0 and gamma 1 are both the same set, which is this set. Right? So if it is a map from this space to that space, 0 interval to that space, then at every time I can take any point t in 0, 1 and it will be a configuration, right? So this, let's say this is time equals 0. Then suppose at time equals 0.3, these points would have moved to 3 different points. But note that this is a continuous function. So as you go forward in time, these would have taken some smooth paths. Like this would have gone here, this would have gone here, this would have gone here, and so on, right? Now let's go further in time. Equals 0.6. Suppose this just goes here, but this goes here, and this goes here. And what is this business with the crossing? Why are these crossings happening? It is because it's our point of view. Like I'm keeping a paper in front of me, then he is behind the paper, right? So in 3D space, when you take a photo, some things are going to be behind the other things. So that is what is happening here. So here, if I take this plane, this might be some plane like t equals 0.4. Here, this point is in front, that point is in the back, that's all. But they are still distinct points. They are not overlapping. But because we are drawing a 2D picture, it looks like they are overlapping. So even when you draw these, take these points to be distinct and moving around, they appear like this overcrossings and undercrossings depending on which is in front and which is in back from your direction of view. Okay, then finally, at t equals 1, these can do whatever they want they have to come back to the same 3 points, 0, 0, 0, 1, and 1, 0. But it doesn't matter who comes where. This guy can go here, that guy can come here, this guy can go here. That's fine. So this is a loop in configuration space. This is what loops look like. And what do they remind you of? Yeah. So in fact, this is an alternate definition of the braid group. Let me just write it big. So another definition, alternate definition of braid group on n strands is Bn is equal to pi 1 of conf n. So as many points as you take corresponds to the number of strands. So Bn will be pi 1 of conf n.
0, 0 is going to 0, 1.
Yeah. Yeah.
0, 0 is going to 0, 1. So aren't the endpoints changed?
Yes, but that same is true of braids, right? If I were to draw this as a braid, so this kind of is a undercrossing. So if I were to draw, so in order to make the correspondence with the braid, I have to take these 2 points, these 3 points suitably. I should take them in one row, okay? But in a fundamental group definition, I'm allowed to choose the base point. So that's one thing I didn't quite emphasize, but it's actually the case that you can take whatever base point you like and you get the same group. So I have to take the starting point suitably. And if I take the starting point to be 0, 0, 1, 0, and 2, 0, so just to simplify life, let me just change this picture. Let me make this 0, 0.5. And they will end up in half comma, sorry, I wanted to say half comma 0. So now this is looking exactly like a braid. If I want to draw the braid picture, this would be overcrossing, and then this does nothing, and then does an undercrossing. So this would have been the braid.
And then it is not a loop. It is not.
Yes, a braid is not a loop, but this one is a loop because the starting and ending points are the same. As an unordered set, as an ordered set, they are not the same. That's it. That's why the unordered is important, because something starting from here can end up there, because the order doesn't matter.
No, madam, your 1 comma half comma 0 ends in 0 comma 0.
Yes, but just carefully look at the definition. What is this definition? At any time between 0 and 1, you need to have a set of 3 points, and that is true. You slice this picture anywhere in the middle, and in the slice, it will be 3 distinct points. So I'm not breaking the definition. Nowhere does it say it has to come back, each strand has to come back to the same one. It can permute. Say it again. Conf n R2 is it's not a discrete topological space. No, n points, but in R2. So they are moving in R2. So it's not a discrete space. So that's kind of the interesting thing. You start out, like in general, the pi 1 will be discrete. So even if you start out with a large continuous space, like our first example was R2 minus a point, which is a continuous space. And from that, you extracted a discrete group. So same thing you're doing here. Conf n R2, it is like n copies of R2 with some stuff taken out, right? Like you're saying that if they are the same, then we are saying that, but it's literally this space has dimension 2n. So it's a 2n dimensional space. And the pi 1 is discrete. Any more questions? Okay, if not, let me just tell you where my talk was going to go and where we didn't get to, which is that there are these other very interesting objects called knots, okay? So that's like literally, let's say that's the part 4 of the talk, which I'll do in 2 minutes. So what are knots? So knots are literally, you take a string, it is sitting inside 3 space, and in the end, you glue the ends together. This is a knot. But you can also do interesting stuff, like you can knot it in the middle, put some more knot in the middle, and then join it. And this is sitting inside R3. So this is a copy of a circle. This is literally a circle like this. If I take a string and join the ends, it's a circle, right? And it's sitting in R3. So all these are knots. And it is, so a knot is a map from S1. S1 is a circle to R3. And a knot is often denoted by the alphabet K. And you can study knots by looking at the pi1 of their complement. You take out the knot from the space and see what remains and look at the fundamental group of that. So that gives you some interesting information about the knot itself. So for example, if you take the trivial knot, which is just this circle, okay, this is sitting inside R3. So if you take this thing, then pi1 of R3 minus K is actually just set, because the generator just goes around. So note that you are not allowed to touch this circle. But going around the circle is something then you cannot contract. So the number of times you go around will give you different elements in pi1. So for the trivial knot, this is called a trivial knot because it's not knotting at all. You just take the circle and join it. So for the trivial knot, the pi1 is Z. The next most complicated knot is the trefoil, which occurred in the title of my talk. And what is a trefoil? Let's just construct a trefoil here. So this is the simplest knot that you have seen, right? And if you join the endpoints, this is a trefoil, okay? And a better view of this is this. So if you kind of tighten this, which I can't do because it's a wire, this is just that knot loosened up a little bit. So this is a trefoil. And the nice thing about a trefoil is, if you draw it on the blackboard, there are going to be overcrossings, undercrossings and all. But if you draw it on a torus, it doesn't intersect itself at all. So this is a torus. You have all seen a torus before, right? It's a shape like a donut or a vada. And if you take this torus, this dotted lines are in the back part of the torus. So the dotted lines and the solid lines are not intersecting because one is in the back and one is in the front. And this thing goes around twice and goes around in this direction thrice. And that's the trefoil. And literally the last sentence of my talk is that pi1 of R3 minus the trefoil knot is B3. which is utterly remarkable. And if you want to learn more, and the proof is quite elementary. If I had like half an hour more, I could have done the proof, but I advise you to go read the proof in this URL, math.ucr.edu home bias, that's a mathematician, week 261.html. So if you just search for braid group Trefoil bias, this is the crucial thing, the name of this guy. So he has these, he puts out like lots of interesting mathematical nuggets, and this is one of the things. And so this is something which is totally accessible with the math you know. So you can go read this, and if you like this, you can also read more of his stuff. It's like, it looks out like every week he puts out something like this. So yeah, I'll stop here. Look in Wikipedia, it's easy. So we wrote down one relation, right? There is just one other easier kind of relation. So, and it's very easy. So I advise you to read more about braid groups on Wikipedia. It's fairly accessible. Yeah. No, that's a good question. And like B2, we have seen, it's the same as the unknown. B3 is this one, but beyond that, there is nothing. In fact, he actually, in this article by Bias, he actually mentions that the higher braid groups will can actually be realized as you take, instead of R3, you take R5, R7, higher dimension vector spaces, and take out knots of higher dimensions. So that's very complicated to visualize. But indeed, it is indeed the case that those are also not pi1 knot complements of higher dimensional knots. But that's not easy to see.
So if I take just a knot, it can be unknotted in higher dimensions, right? Like,
yes. But that, when they're saying that, they mean a higher dimensional knot. So in 3-dimensional, you can't unknot something 1-dimensional. If you take something 5-dimensional and 3-dimensional sitting inside it, then you cannot unknot that. Yeah.
Any more questions? Let's thank the speaker again.